will be received at the receiver antenna. So the receiver, there will be another antenna here, the receiver. And remember, this antenna transmit at the high frequency band, like gigahertz, megahertz, and this receiver antenna receive at the same frequency, gigahertz or megahertz band, depending on the channel. The transmitter antenna and the receiver antenna, that operating frequency band always based on the channel frequency band. Suppose I transmit my voice signal. The receiver antenna here receive the modulated signal of my voice message. Now remember, the received signal at the receiver antenna is at a gigahertz or a megahertz high frequency band. Suppose, thinking about the message signal being transmitted here at the receiver antenna, and if I try listen to the output of the signal from this antenna directly, I wouldn't be hear anything because the signal is at a gigahertz band and we cannot hear it at all. So somehow at the receiver, after the modulated signal been received at the receiver antenna, we need to do something at the receiver such that we can hear the baseband signal. In this case, that's a voice signal here. And this process is the demodulation at the receiver part. Now, the demodulation scheme at the receiver, depending on how the message being modulated at the transmitter. For example, if we sitting in the car, we want to listen to the AM radio, you have to push the button for AM. And then if we want to hear the FM radio, you probably have the button for FM radio. So you can see AM and FM, they're modulated differently, they demodulated differently. So there are two sets of different circuit in the AM and FM, for example, in our car. The same thing here for DSBSC here. This is a modulated signal. We multiply the message signal directly by the carrier signal. This is a diagram. How do we implement that in transmitter? What about receiver? Suppose if this is received at the receiver. So at the receiver, the received signal RT equals to U of T. Assuming the channel is ideal, channel just equals to 1, which is never happened in real life. And how do we get the original signal? That's the message signal. This is a demodulating scheme for DSBSC signal. This is a received antenna. The received signal RT equals to U of T because we're assuming that the channel is ideal. So at the receiver, we're going to multiply by the same carrier frequency with FC. But at the receiver, there may be a local phase shift, so we include a phi here. Then after multiplication here, this is a multiplier. After that, we do low pass filter. The output of low pass filter is proportional to the message. Proportional is not equals to the message directly, but it's proportional. Is the magnitude can be up and down for some amount, but the shape is the same because it's proportional. You can see here the output is scaled by half AC and scaled by cosine phi. Phi is a local phase at the receiver. Now let's do some calculations. The output for the multiplier is y of t. Y of t equals RT multiplied by this local cosine signal, cosine 2 pi of C of t plus phi, and plug it in. RT equals U of t, so this portion is U of t, the modulated signal. And then cosine multiplied by cosine, we use trigo identity. So there's a half at the front. So the angle, take the difference first. So that's cosine phi. And then the angle, take the sum. That's 4 pi FCT plus phi. And then MT empty, this term still here, and this is still here. So this is the output of the multiplier. And this signal will pass through a low-pass filter. If we look at the signal here, 2FC, that's the frequency component for this cosine signal here. So this whole thing has the frequency component centered at double of FC. So that's a high frequency. So if we pass this whole signal y of t into the low pass filter, this portion, the high frequency components, will be filtered out. So we're going to have this portion left. Supposing that the gain for the low pass filter is 1, so we don't amplify the signal, or we don't attenuate the signal, just for ideal case, so that the output will be half AC empty cosine phi. This is exactly what we obtained here. I call it YLT. L means low pass. So we just look at everything in time domain. Let's look at the frequency domain here. Y of t is equal to this. We're going to use modulation property. We're assuming phi equals 0 for ideal case. And the transmitter is exactly synchronized, and then we're assuming that phi equals 0. And we want to plot the y of f, the frequency component of this multiplier here. We can use modulation property. This is phi goes to 0. This is RT, which is U of t. And then we can use the modulation property that this whole spectrum move to FC. So this spectrum, remember there's two components for the negative frequency and positive frequency. So this portion, 0, will become FC here. And this FC here will become double FC. And this is this portion. And this portion will move to 0, right? So 0. This here. And this here. Okay, so this spectrum moved to FC. According to the modulation property, this spectrum moved to minus FC. I'm going to plot it here. So yeah, we'll see this portion will move to minus 2 FC, right? And this portion will move to 0. So using different colors, I'm going to have illustrate different colors. This portion will be this portion, and this portion will be here. And then you sum them up. So that's what we have it here. I have this portion that's come from here, and this portion is coming from here. And this plus together, I have another color here. Okay, so that's this plus this. And then if I apply a low pass filter, a cutoff frequency, as long as a cutoff frequency from anything from here to here, that's fine. And then I can obtain this spectrum. And this spectrum is the message signal, because look, this message is modulated to FC, and minus FC was a message signal. That's the message sitting at 0, exactly the same shape. So from time domain and frequency domain, we justify this demodulation scheme here. Let's do a little summarize here. At the transmitter, the modulator is that if we have a message here, we modulate with a carrier C of t equals cosine. And then we have U of t. And then you launch to the channel. Channel, we're assuming that's ideal, right? At the receiver, we're going to have RT that equals U of t, exactly received the modulated signal. How do we demodulate the signal? We multiply by a local cosine signal with the same frequency and with a phase shift, local phase shift. And then we do a low pass filter. This is the signal we obtain. The signal at the output here is proportional. You can see here is proportional to cosine phi. And phi is the phase difference between the carrier signal and this cosine signal at the receiver. Okay, let's say if phi equals 0, which means that this carrier at the transmitter and this cosine signal at the receiver is perfectly synchronized. And although it is very hard to do, but somehow let's assume it is synchronized. So phi equals 0. In this case, this is exactly proportional to MT without any other parameters. What about phi equals to 45 degree or negative 45 degree as plus or minus pi over 4? Then cosine pi over 4, that's 1 over square root 2. So in this case, you can see the message has been degraded by 1 over square root 2, but still okay. What about phi equals to 90 degree or minus 90 degree? That's plus or minus pi over 2. Then the output is 0. We don't get anything. We lost the message signal. No matter what we do, if phi equals to 90 degree, that's this case. That's this case. Then the output at the demodulator is 0. So we can say to recover the message efficiently, we want the phase to be synchronized between the transmitter carrier and the demodulator at the receiver. So how do we do that? There is sometimes we use phase locked loop. There's a section 6.4 in our textbook. We're not going to go to the detail of section 6.4 due to the time constraint. Or at the transmitter, or in the modulated signal at the transmitter, we add a small portion of cosine signal here. So this is a DSBSC components here. That's a carrier multiplied by the message. And then I'm going to add a small portion of cosine FCT. This is a carrier. This contains the phase information for the transmitter. So at the receiver, when I receive this signal, I will extract this portion at frequency FC. So I can obtain the phase information contained in this portion. And I use this phase as a demodulator. So these are the typical two ways to achieve the synchronization of the phase between the transmitter and the receiver. In lab 4, we're going to perform the demodulation of DSBSC signals. That's this scheme. So to demodulate the signal, we need to modulate first. So you're going to have a multiplier to generate the modulated signal here. Then this signal will to pass another multiplier, and this multiplier multiplied by cosine signal with phase shift. And this phase shifter can be adjusted by a potentiometer, but without digital reading. And it's just a knob. And we don't know what is the phase in the cosine signal here. So what do we do? The lab is set up like this. I would like this output goes to 0. So if this output goes to 0, theoretically, the phase difference should be 90 degrees, right? So now you adjust this potentiometer in the lab equipment such that here goes to 0, the output at the low pass filter goes to 0. And then you measure the phase difference of this carrier and this carrier. Suppose if we have this two cosine signal, I draw it here. So this is 0 time. And now I have another one, and this is the same time, but with some phase shift. And this is 1. And now this signal has this now. So now you can see if this is a 1 and this 1, you measure the time difference here. This is a delta t. This is a delta t. So what's the phase difference between these two waveforms? That will be, we know the frequency, right? The angle will be 2 pi fc, the same frequency. The frequency is fc, and this time difference, let's say delta t. So this will be the phase difference phi. And this is how do we measure the phase difference between two waveforms in lab 4.